Hermle. He will speak on the structure of non-compact operator semigroups. Please.
Okay, thank you. Hello, everybody. Thank you for the opportunity to talk here. And today I want to present a small structure theorem, which I've written down in my master's thesis. And before I formulate the theorem and sketch the proof, I want to talk a little bit about the underlying method or in philosophy. And this is more or less the JDLG splitting method. Okay, and JDLG stands for Jacobs, Deleuze, and Klicksberg, which introduced this method. And roughly speaking, the idea is you have an operator semigroup on a Banach space, and you take the compactification with respect to an operator topology, and then use the compact structure to split the Banach space in two parts, on which the semigroup restricted behaves well. And more concrete, for example, in our case, we take look at the following operator semigroup, just the time discrete one. For example, you can keep this example in mind for the whole talk. And we take, okay, this is just an operator semigroup on the Banach space E, and we take the norm closure. And we require that this norm closure is compact. So this set is it's a compact topological semigroup. So, okay, we have this structure, and we try to use this structure to split our Banach space in two parts, such that the semigroup restricted to the first Banach space, to the first subspace, is nice structured. And the semigroup restricted to the other is is stable. Okay, with stable, I mean just for example that the zero operator lies in the restricted semigroup on E1, and this is equivalent to the fact that the power of the operator restricted to the subspace E1 converges in the norm to zero. Okay, this is the classical notion of stability of a semigroup. Okay, this is the underlying idea, this dichotomy between structure and stability. And yes, the following theorem is a theorem of this type. And this is a very good tool to analyze, for example, the asymptotical behavior of a semigroup. Okay. So now I will directly state the theorem, and I will do this in two parts and then sketch the proof, because I think the proof is more or less nice because it's elementary and it uses nice structure theory. So the next part is the structure theorem. Okay, let T be now we directly take abelian relatively compact semigroup. So then the theorem says the following. Okay, there exists a projection in the norm closure of T. Okay, I call this norm closure S. And this is then a compact topological semigroup. Okay, and in this compact topological semigroup, we find a projection. Okay, and this projection is then bounded. And so it split the Banach space directly in two parts, in the range and in the kernel. Okay, and the statement of the theorem is now the following. Okay, when we restrict the semigroup to the range of this projection, then it's a compact topological group, which is isomorphic to an n torus times a finite abelian group. Okay, this gamma is a finite abelian group. Okay, and this is a very nice structure and very easy structure. And the second part, okay, is more or less trivial when you restrict the semigroup S to the kernel. Okay, then the zero operator lies in this restricted semigroup. Okay, and this is trivial because we know that our projection lies in the semigroup S, and when we restrict the projection to its kernel, then the zero operator lies in the restricted semigroup. So what we want to show is the first part. And for this first part, we use now the structure of this relatively compact semigroup. And I will sketch now the proof. And yeah, I think it's more or less elementary to follow. Okay, proof. The idea is now to find in this abelian relatively compact semigroup a compact topological group. Okay. So what is the candidate for this compact topological semigroup? Okay, we use the ideal structure of this compact semigroup, and the candidate is for this topological group is the minimal closed ideal in this semigroup, in this compact semigroup S. Okay, we have to show that this minimal closed ideal exists. And how we show this, okay, I call this intersection over all closed ideals K. And when this intersection is not empty, then it's clear that K is the minimal closed ideal. So we have to show that it's not empty. Okay, and now we use the compactness of the semigroup in the following way. Okay, take a finite set of closed ideals. Of S. Then we can intersect these n ideals. And in this intersection, it lies the product, or the product of this intersection of this n ideals lies in the intersection. And because each element of this product is an ideal, so this is not empty. And it lies in this intersection because the semigroup is abelian. So we have showed that this finite intersection is not empty. And now we use the finite intersection property of compact sets. And so we get that K, the intersection over all closed ideal, is not empty. So this minimal closed ideal exists. And now we use the structure of this closed ideal to show that this K is indeed a compact topological group. Okay. And I will sketch the simple elementary arguments also too. Okay, this is the second part of the proof. Okay, show K, the closed minimal ideal, is a compact topological group. Okay, and it's clearly abelian because it's a subgroup of an abelian compact topological group, a semigroup. Okay, the compactness is trivial because we know that K is closed, so it's a closed subset of a compact semigroup, so K is clearly compact. And it's also clear that it's a topological abelian subsemigroup of S. So it's a topological abelian semigroup. So the only thing we have to show is that it's a group. So we have to show that there exists a neutral element, and for every element there exists an inverse. And we have to show that the inverse mapping is continuous. Okay, that the inverse mapping is continuous, it's a short exercise, but that, for example, there exists a neutral element. In K, you see, you can use here the ideal structure of K. So for example, the idea is take an arbitrary S in the compact semigroup. Okay, and then take a look at the set S multiplied with K. So this is just a set of all products with S with all elements in K. So this is again an ideal which lies in K. But because the multiplication is continuous, this is a closed set. So when you use the minimality of K, okay, Okay, we know that these two sets have to be the same, and this equality implies that there exists an element Q in K such that SQ is the same like S. And with the same argument, we see that the set, KS is the same like K, and this implies that for all R in K, there exists an R prime in K such that R prime S is the same like R. Okay, now we use these two equalities and we get the following. Okay, when we multiply an arbitrary R with Q, then it's the same like R prime S Q, and this is the same like R prime S R with the first equality. And so we got R, and this indeed implies that Q is the neutral element in the semigroup K. And with the same argument, we can show that every element in K has an inverse. This is completely analog. So we have showed that this minimal ideal is indeed a compact topological group. And this is very nice because for compact topological group, we have a very big theory, so-called harmonic analysis. We have many nice structure theorems. For example, the existence of a Haar measure, so we can integrate. We have the Pontryagin duality. We have the Peter-Weil theorem. And these are many strong theorems that we can use now to analyze the structure of K, for example. Okay, now the third part of the proof. Remember, we want to show that the semigroup restricted to the range, okay, of this neutral element or of this projection. Okay, it's clear that it's idempotent because it's a neutral element, is isomorphic to an n torus times a finite abelian group. Okay, how we can see this? Okay, this is not okay. This is maybe the most difficult part of the proof. Okay, it's again clear that the minimal closed ideal is because of minimality the same like the principal ideal which is generated by the neutral element. And now this group is via restriction isomorphic. Okay, you just take the operator and restrict to the restricted semigroup to the range of Q. Okay, so this is a semigroup of bounded operators which lives on the range of Q. So, and this here is, because this is an isomorphism, then a compact topological semigroup. Group, sorry. Okay, this is the compact topological group. So, and now there's a nice key lemma which identifies precisely the structure of this group. This is the key lemma of the structure theorem, which says, okay, when you have an operator semigroup, when you have an operator group of a Banach space, which is compact with respect to the norm topology, then this group is a Lie group. Okay. So this key lemma is not completely obvious when you see it for the first time, because, okay, when you know the classical definition of a Lie group, it's a purely analytic one. So for example, it's a group object in the category of differentiable manifolds, okay? But this is not very useful, this definition. So you need a nice characterization, and there is a nice characterization. There's a characterization in purely algebraic topological terms, okay? And this characterization is, okay, G is a compact Lie group if and only if G has no small subgroups, okay? And in our context, this just means that you find an open neighborhood of the identity operator such that the only subgroup of G which lies in this identity neighborhood is the trivial group. Okay, and with the help of this definition, you can prove an abstract theorem, for example, that every subgroup of the group of the invertible elements of a Banach algebra has no small subgroups. And this indeed implies this lemma, that G is the Lie group. Okay, you have to work a little bit for that. But when you know that, okay, you can directly you can directly plug in our, or you can directly apply it to our restricted semigroup S range Q, because this is a compact topological group of with respect to the norm topology of the linear bounded operators on the range of Q. So this key lemma implies that the restricted semigroup on the range of Q is a Lie group. It's a compact Lie group. Or it's a compact abelian Lie group, because we are always in the abelian setting. So this is nice, because now you can go to Lie group theory and can look up the classification result about Lie groups. And now there is a nice theorem which states that the compact abelian Lie group are very easy. So because G is, okay, let G be a compact Lie group, then G is abelian if and only if G is isomorphic to an N torus times a finite abelian group. And this is exactly what we want, okay? So the main idea is just to identify this restricted semigroup as a Lie group and then use abstract Lie theory to get that this restricted semigroups is just a product of an N torus times the finite dimensional abelian group. So, and this theorem, okay, it's not so easy to prove, because you need your harmonic analysis, you need the projective structure of compact groups, and then you use the Pontryagin duality to get a theorem. Okay, so this was the first structure result. Okay, we can restrict this semigroup, this abelian compact semigroup to the range of Q and get a very structured asymptotical behavior. So, and the second structure theorem, I will just mention it for completeness, about non-compact operator semigroup is the following. Okay, we now want to know what is the precise structure of this range of Q. Okay, how does this Banach space look like? Okay, take again an relatively compact, okay, with respect to the norm topology, abelian semigroup. Then then you get again a projection, and you can now say what the range of Q is. Then the range of Q is the same like the direct sum, okay, over the following spaces. This spaces on which the semigroup T acts like a character of the semigroup. Okay, so I write this down. Okay, a character of a semigroup is just a continuous group homomorphism from the semigroup to the torus, a semigroup homomorphism from the semigroup in the torus, and okay, these are just these spaces where finitely many of these characters these are just this space where the semigroup acts like finitely many of these characters. So, and to make it a little bit more concrete, then for example, T is just the time discrete semigroup, then the range of this projection is just the direct sum of finitely many eigenvalues or eigenspaces. Okay, so this is the structure of this range Q. So this is the second structure theorem. Okay, and for the last few minutes, I just want to say which operators are structured in the following sense. Okay, which operators generate a non-compact operator semigroup? Okay, for which generator this group is compact. And the theorem is the following: that T be a power-bounded operator. Okay, then this semigroup ST is compact if and only if a spectral property is fulfilled, and this is just a property that the spectrum intersected with the torus consists of poles or is empty. Okay, so the operator which generates a non-compact operator semigroup have a spectrum of this form. Okay, they have spectrum in the interior of the unit disk, and on the unit circle they are just poles. Okay, and concrete examples, concrete operator classes which generate such an operator semigroups are, for example, compact operators or power-bounded compact operators, or power-bounded quasi-compact operators. So an operator is quasi-compact, or T is a quasi-compact operator if there exists an N and the compact operator K such that the operator norm is smaller than 1. And for example, also positive operators on a Banach lattice with one-dimensional fixed space. One-dimensional fixed space. For which one is a pole of the resolvent. So, and these are typical operator classes which generate such non-compact operator semigroups and to which you can apply the structures here. Okay, then this was everything I wanted to talk.
Thank you. Are there any questions or comments?
Yeah, maybe I have a question. So you mentioned this characterizations of compact Lie groups. So where can one find these? So is there a good reference?
Yeah, I think the best reference I know is the book of Karl Heinrich Hoffmann, The Structure of Compact Groups. Here the whole Lie theory is very good written down, and you can more or less find this classification results of Lie groups, and also this result that also this operator theoretic approach to Lie groups you can find out very well, I think.
Okay, thank you.
More questions?